How was everyone's projects? Was it like an interesting task, at least? Yeah? Did we get to try different methods? And was it challenging? Was it too hard of a data set? Did it make sense, like semantically? Project. This is the first time we're using this data set, so we're trying to get some feedback on if we should keep using it next year. Yeah? You like that? Okay. Cool. I'm really looking forward to reading everyone's reports because let's see here. This is the current leaderboard for this project. I really like the names, by the way. I appreciate the names. I like that Emil and I both made it onto the team names. So thanks for that. I'm on here somewhere. Yeah, I'm down here. Yeah. Anyways, yeah, I'm really impressed by everyone's kind of performance. I did not expect 0.9. I didn't think we would hit 0.9 based on my own work. I actually barely made it above 0.8, I think, but I only had like a couple hours to work on it. But yeah, so either everyone's doing really well because because of the merits of your methodology, or you're peeking into the test set a little bit. So we'll see. We'll read your reports and figure that out. But I'm sure there's a lot of good ideas on here. So anyways, yeah, as someone who's this was like their actual research project, of which this classification was a small part of, but it'd be interesting if there were some features in here or methodologies that our team didn't think of before that we could implement ourselves as well. So again, really looking forward to your reports, and remember your report is 90% of the grade and not your Kaggle performance. You will get a extra credit for being high up. I guess like the top 50% will assign like anywhere from 1 to 5 points of extra credit. If you're first place, you will get more extra credit, obviously. So yeah, focus on your reports. If you haven't started your report yet, you should probably start because that is due tomorrow at 9 p.m. So again, Kaggle leaderboard closes at 5, but this is just for clout, I guess, and it's only about 10 points of the actual grade. And then the rest is your report. And then I should also mention, I believe the assignment mentions that you should also be sharing your collab notebook afterwards with us and with the rest of the course, so we can all kind of see what each other did. And particularly if you're kind of in the top 5 or top 10, I recommend giving some effort into your collab notebook and or your report so that you can kind of talk about how you managed to do so well on the project. And then, if there's some novel ideas in there, we can talk beyond just the course project submission. But anyways, so yeah, thanks everyone for putting your effort into this. I know sometimes projects like these can take more effort because it's so open-ended. So sometimes it's more work than just homeworks where you can finish off a question and you're done. This is kind of your ambition is your limit, which is why we also set a time limit on this before the report, because we know if we set the deadline for both, then you're going to be working on the leaderboard right up until the deadline and not paying any attention to the report. So that's why we have 2 different deadlines. Yeah, anyways, again, looking forward to everyone's results on this, and thanks for working on this, and I hope you liked it. We have a couple more of these coming up with Project 2 and Project 3 that are also kind of creative and interesting, so yeah. Any questions? Yeah?
Oh yeah, so I just had a quick question about I just wanted to double check what's due today at 5 p.m.
Mm-hmm. Yeah, just the Kaggle leaderboard closes at 5 p.m. Your report and your collab notebook, I'm pretty sure, is due at 9 p.m. tomorrow. Yeah. But we're just stopping submissions so that it's a forced deadline, so that we force you to work on your report for a full day at least, basically. Yeah?
Does the collab notebook need to show how you arrived at all its submissions, or just whatever the one that
Just whatever the one that was scored.
Okay.
Yeah, so just a collab notebook just to demonstrate your best method.
Okay.
Yeah. If you want to show more, that's fine, and I think we have some extra credit space too. Like if you demonstrate all of your models, we'll probably give you extra points or something like that, but just for full points, you just need to show how you arrived at your final model. Yeah, pretty sure, yeah. And any additional graphs and visualizations, or if you have a confusion matrix on your validation data set, or a ROC curve or a precision recall curve, any kind of additional stuff you can include, it'll all help towards getting that maximum grade. Yeah, just kind of treat it as an actual report. Yeah.
Problem set 4.
Problem set 4 is out. pretty sure on Wednesday. Let me check. Jeez. Homework 5 is out on the 14th, so it's supposed to be today. It might get pushed until tomorrow, in which case we'll adjust the deadline, but it's supposed to be out today. I'll follow up with the TAs on that. Thanks for asking. Okay, and yeah, everything else is on the website. I just can't get to it from Firefox because, anyway, all right, that's enough of that. Okay, any other questions regarding the project one or the next homework? Okay, great. Let's start with the lecture then. Okay, so today's lecture is on latent factor models and non-negative matrix factorization. A little bit of a disclaimer up front. I don't have a background in this, so this is kind of actually Professor Yisong Yue's kind of not his specialty, but he's done work in this field. This is a fairly, in my perspective, a fairly niche field, but I'm really glad that he's dedicating a lecture to it. It also has meant that I need to learn all the material from scratch, and you're in danger when the lecturer shows up with 8 pages of handwritten notes. So we're all going to get through this together. I will do my best to explain everything. It is also very dense linear algebra in a linear algebra sense. So there's going to be a lot of technical kind of linear algebra concepts that we need to kind of formalize everything. So if you don't have a linear algebra background, I'm also going to try to kind of add intuition on top of it. So it's okay if you don't understand all the formulas that are presented today. There's going to be a lot. But even if you don't get all the equations, I'm going to try and build that intuition, and then you can come back to the slides later and kind of understand the actual math behind everything. Okay? And then I believe the homework is going to have a bunch of this as well. So eventually you're going to have to understand it, but if during the lecture you don't get it, just kind of understand via intuition, and then come back to the formalities or come back to the formalism afterwards. And if you have any questions, just, again, raise your hand or just ask the question right away. And don't hesitate to do that if you don't get something, because that doesn't mean that you're dumb. It means I didn't explain it properly, right? Because I'm also just learning this. All right. So let's get through this lecture, and I think it really is very interesting. It's a very interesting section of machine learning. So I am excited to share this with you. Okay. So today we're going to first start off with some useful matrix properties, and then we're going to contextualize it afterwards. So we're going to start with some we're going to start by defining some terms, and then you'll see how it's useful in the things that we're talking about afterwards. So just stick with me through the initial definition stage here. So then after that, we'll use the things that we covered initially to talk about latent factor models and non-negative matrix factorization, and you'll know what that means by the end of this lecture. Okay, so we're going to recap the previous lecture real quick, and I will say, so the previous lecture we talked about, and it's been a week, so we talked about clustering, right? And then we talked about PCA. And the kind of idea of that lecture was, in an unsupervised learning sense, there's value in representing the data in some lower dimensional space, right? So in clustering, the lower dimensional space was membership. So like these are the clusters, and these data points are members of these clusters. And then for PCA, we actually projected the data into a lower dimensional subspace in which we can deal with that data in the lower dimensional subspace, right? So we're kind of reducing the dimensionality of the data while trying to keep as much of the variability or the variance as possible. So just to recap, and then at the end of last lecture, I skimmed over SVD, and I shouldn't have done that because this entire lecture is just SVD. So I'm going to cover this at the beginning of this lecture so that you're not missing that context. Okay? All right. So just to recap, so we talked about orthogonal matrices, and a matrix U is orthogonal. And if you've done lineage, you already know this, but I'm covering this again because not everyone has the same background. But a matrix U is orthogonal if U times U transpose is the identity matrix, etc. In a more kind of a easier to understand way, it means each column of U, or each column of U is orthonormal, right? So every column of U is orthogonal to each other, and when you multiply them, you get their norms are 1. That's all that means. So therefore, a matrix U actually can define a transformation into a new coordinate space, because again, each kind of column can be its own kind of almost basis vector, right? And they're orthogonal to each other, and they're norm 1, and so they don't stretch the data in any way. It just transforms the data into a new coordinate space, right? So again, for any column U, U transform times U is 1. For any 2 columns that are, so if you multiply a column by itself, it's 1 because norm is 1. If you multiply a column by any other column, it's 0 because they're orthogonal, right? They're perpendicular. So we can interpret U as a rotation matrix or a transformation matrix, and then U transpose is the inverse rotation. And another property of orthogonal matrices is that U transpose is equal to U inverse, right? And that's why we can do that. We can transform and then transform back. That's why that works. All right. So again, during the lecture last week, I did this, right? So like U and then like U transpose, back to its original coordinates. So then the context in which we talked about it, especially for PCA, is that any subset of the columns defines a subspace. So if you calculate U and U transpose and the dimensions are exactly the same, you transform and then you transform back and all the data points stay the same. But if you only use a few columns of U, right, then we're projecting the data onto a lower dimensional subspace. So we kind of, in PCA terms, we said that we can find some orthogonal matrix U so that these axes capture as much of the variance as possible, right? So if we pick the top K, right, axes that can express the variability of the data, then we can represent the data in a lower dimensional subspace while still keeping all the properties of the data, right? So again, U transpose X transposes into a new coordinate space, and then doing it back transposes it back. But we lose all the information that we lost when we dropped those other columns.
So are you literally just comparing the variances of each column to determine which the best feature is?
So when you do PCA, and we'll talk about this when we cover SVD2, the columns are sorted in a way so that the first column always captures the most variance, and then the second.
Is it just comparing the actual variance, or is it another measure? I think it's just variance of each column, right?
Not really. So we're measuring the loss, this residual loss of how much information we lose when we project it back. So let me get through these slides and see if that makes sense, and then we'll talk about it. Okay. Sorry. So what's being expressed here is when you drop a column like this, right, and then you project it onto a lower dimensional subspace. When you project it back into its original dimensions, we lose some information, right? And so what PCA and SVD tries to do, right, singular value decomposition, is when you calculate the SVD of this vector, we're guaranteed that the first K columns of U minimizes the residual of when we project it back into its original subspace. So that's one interpretation. Does that kind of answer your question?
Yes.
Yeah, okay.
So you're trying to check to see, after you project it back, how much of the space contracts.
How much of the information we lost. So how well we can reconstruct.
It's
literally just norm 2.
Determinant,
would that be the determinant? In what sense?
Because it's the measure of the actual space contraction. Is that what you're going to be comparing to see how much information you lost? Or is there
It's literally just the norm 2 loss. Yeah, per data point. I know what direction you're going, but that's another interpretation. We're just going to stick to this for now just to keep it simple. Okay. All right, so singular value decomposition, and I kind of glossed over this last lecture, and I really shouldn't have again. But SVD is this property of matrices that says for any matrix, and this matrix can be rectangular, right? It doesn't have to be a particular shape. It doesn't need to have any special properties. For any x, we can decompose this matrix into these three matrices: U sigma. Is that sigma? Yeah, sorry. U sigma V transpose, right? And this decomposition has the property that U is orthogonal, V transpose is orthogonal, and sigma is diagonal. Okay. This is just a property. We found out that any matrix can be decomposed into this kind of form. And this is really useful because, again, we can treat U as we did before. We can treat U as this kind of orthonormal matrix, which we can use to transpose data into a lower dimensional subspace. So SVD is great, but how do you actually come up with these matrices, right? The way you come up with these matrices is via PCA. So let me walk through this real quick. So we want to find this U sigma V, right? We want to calculate this decomposition because we know this decomposition is possible for any matrix X, and we can do useful things with this U sigma V matrices, right? And that's because SVD has this property that whatever the first k columns of U we use, that kind of transformation that those columns of U define guarantees that it minimizes this residual, right? This reconstruction residual, where we project it into this KU subspace, and then we project it back, it minimizes this residual. So SVD is very useful, and we want to find this matrix U. The way you actually do that is by doing PCA. PCA is different because PCA works on the covariance matrix of X. Okay, so we do X times X transpose. And if you know anything about covariance matrices, it's that, right. Yeah, so when you do X times X transpose, this term on the left becomes positive semi-definite, and it's also symmetric, obviously, right? And so when you do that, we can find the eigenvalues and the eigenvectors of X times X transpose very easily, right? So when we do that, we come up with the eigendecomposition of X times X transpose, which is U times lambda times U transpose. Okay? So using that, because that's easier to calculate, right? It's because we know how to calculate the eigenvalues and eigenvectors of a square positive semi-definite matrix. We can use that to calculate the full singular value decomposition. And the way we do that is by showing that these two are equivalent, actually. So if you take X times X transpose, and then you break each of them down into their SVDs, right, into their singular value decompositions, because of matrix arithmetic properties, eventually it collapses down to U times sigma squared times U transpose, right? And then if we flip this, if we do X transpose X, it also decomposes down to right? So then we get V sigma U transpose, U sigma U transpose. This is just the identity matrix, right? So then we get V times sigma squared V transpose, right? So now we have V, we have U, and we have sigma, right? So you actually use PCA to calculate SVD when you're trying to find U and V. But usually, for a lot of the things that we do, we only care about U. So we're good just calculating PCA once and just using that U matrix, and then we're good to go. Okay, so that's kind of the relationship between PCA and SVD that I kind of glossed over last time. But that's kind of the important part. So let me see here. Kind of pegging this to an actual example. Wait, hold on. Let me make sure I covered everything I wanted to cover there, because yeah, okay. Right, and just to confirm that everyone understands eigendecomposition, right? Each column of U is an eigenvector, and each diagonal element in lambda is the eigenvalue, right? So that's why it's easy, because we know how to do that. Okay, does that make sense? Does that kind of connect PCA to SVD for everyone? Okay, we're just going to talk about SVD going forward in this lecture, because that's what actually matters for the models that we're talking about going forward. But if you ever ask, like, how do you actually come up with U? You do it by finding the eigendecomposition of the covariance matrix. Okay, all right. So let's kind of peg this to this eigenfaces example that we had last time. And remember, I did this with PCA, right? But Professor Yusong did it with SVD, and now I know why, because it's important for this lecture. But again, each column of U is some eigenface, right? And this is the same U that you get with PCA. We're just presenting it in the SVD form now. So each column of U is an eigenface, and each column of V transpose is the coefficient per student, okay? So this is like, if we have some big matrix of everyone's kind of face profile images, right? We can decompose this X into U, where these are kind of these eigenfaces, these axes that we've learned, and then each column here defines a student. So if I if you do up this multiplication, right, each person's complete face turns out to be a literal linear recombination of these eigenface columns. Okay? So it is an actual, I think at the end of last lecture, someone asked me about what do you mean by linear combination, and I kind of hedged on it because I was talking about it in PCA space. When you talk about it in SVD space, it is literally a linear recombination of eigenfaces because we have V. Right? When we did PCA, we didn't have V. And we were in like covariance matrix space, so like that's not interpretable. But when you put it this way in SVD form, it makes direct sense. It's a literal linear recombination. Okay? Cool. Okay, any questions on the recap for the previous lecture? Okay, all right, so on these foundations, we're now gonna start to build. We're gonna start doing that by talking about matrix norms. So this is a kind of a new concept, and we're gonna, again, try to build some intuition for these concepts. So the same way we have vector norms, right? We have like Euclidean norm, we have L1 norm, etc. We have similar norms defined for matrices, so for two-dimensional matrices. So we have, well, not two-dimensional, but for matrices in general. So we have the Frobenius norm, pronunciations be rough this lecture, guys. We have the Frobenius norm, and we have the trace norm, okay? So the Frobenius norm, and this is the most classic kind of norm that people generally use for matrices, is the square root of the sum of squares of the entries. So let's look at this definition in the middle first. So you just take every entry in the matrix, you square them, you add them, and then you take the square root, okay? So it turns out that you can show that that's actually equivalent to taking the sum of squares of the singular values and taking the square root. What do I mean by singular values? Singular values are the diagonal elements in sigma of the SVD. It's also equivalent because of this PCA thing. It's the square root of the eigenvalues. Okay, so if you just yes, it's the square root of the eigenvalues. So you can think when I say singular values, square root of the eigenvalues. But we're just in SVD space now. We're not talking about PCA anymore, right? So we can show that the Frobenius norm is defined that way, and that's kind of the traditional norm of a matrix. And this comes in again. This will all be used in the future slides. We're just defining these terms, and then we have the trace norm, which is the sum of absolute values of the singular values. So we can actually show that each singular value is guaranteed to be non-negative. So when you do this SVD singular value decomposition, right, each value in this diagonal of sigma, we can show that they're always going to be positive. So we kind of drop the absolute value here, but you just add all the singular values in sigma after you do SVD on a matrix, and that becomes your trace norm. Okay? The trace norm is also equivalent to x transpose x, the square root of that, and the trace of that matrix. The trace is defined as the sum of the elements on the main diagonal of any square matrix, right? So x transpose x immediately makes it a square matrix. We take the square root, and then we take the trace of that, and that's equivalent to the singular value definition. Okay, so we're going to prove that. And this is a fairly strict, it's not even a proof, it's just a definition. So this is a norm, so we always use the square, whenever we use the Frobenius norm, since it has that square root, like that's kind of annoying. Like computationally, it's not expensive, but it's like an additional step that we don't really need. So a lot of times we will use the square of the Frobenius norm. Same way where like when you use the Euclidean norm, you often use a square of the Euclidean norm because you don't want to do that extra square root step. It doesn't really change anything. So a lot of times you'll see it in this kind of notation where you have the double bars, Frobenius defined on the bottom, taking out the trash, and then square on the
because you
top.
care about like the relative rankings.
Right, exactly. Yeah, for the norms, yeah, we just care about the relative values. Yeah, exactly. So we can actually show that this is equivalent by taking our trace definition initially, and then taking the SVD. I shouldn't say SVD decomposition. That's like ATM machine, right? The SVD of X, and then just doing matrix algebra until you end up at the singular value definition at the end. So we're just showing that these two things are equivalent, and it's actually relatively a straightforward definition. And again, by convention, each singular value is guaranteed to be non-negative, so this works. We should point out, this step here, there's a property of the trace, which is that it's rotationally invariant, which is cool that you can, as long as the matrices in multiplication are rotationally in the same order, the trace is equal, which I think is like a cool property, and I'm sure you can like kind of prove this, but this is just the property of the trace of a matrix, and then that comes into play when we're doing this proof that the square of the Frobenius norm can be described in these two ways. Okay. All right. Okay. So again, all you need to know for the Frobenius norm, the important part, is that the square of the Frobenius norm, which is what we use normally, you can either define it as the sum of the square of all the values in the matrix, or the sum of the square of all the singular values. That's all you need for the Frobenius norm. All right, let's talk about the trace norm. So, oh wait, hold on. Is there one more? Oh, that was the next slide. Okay, great. Yeah, you just need this. That's all you need for the Frobenius norm. And this is useful for regularizing matrix models because we've talked about L2 regularization before, right, in kind of the earlier lecture 3, lecture 4s. So this can be used kind of in a similar way. The intuition is that this is kind of equivalent to the L2 norm. We'll talk about that a little bit more. All right, what slide is this? 11. Wait, no, we're talking, wait. I'm like a slide ahead. Or we're missing a slide. Oh, we're one slide back because of, shoot. Oh, I confused these, okay. All right, let's back up here. My slide numbers are off because, anyways, I deleted a slide and I didn't update the slide numbers. Okay, that's the Frobenius norm. Let's talk about the trace norm now. It's the same way. The trace norm, it's the one with the asterisk on the bottom right. Don't ask me why. I don't know why we've come up with these definitions. But the trace norm, again, is either the sum of the singular values, and this should be the absolute value of the singular values, but the singular values are guaranteed to be positive, so we just say the sum of the singular values. And that's the same thing as the trace of the square root of x transpose x. And again, we can prove that by replacing x with its singular value decomposition, doing a lot of matrix algebra, and then ending up at the sum of all the singular values. Okay, so we're just showing that these aren't random. Like we can actually do matrix algebra to get from one to the other, and that's defined by SVD, which is why I said SVD would be important earlier. Okay. So kind of going back to what I said before, the Frobenius norm you can interpret as the squared norm, right? Because it kind of has analogs to the Euclidean norm and the vector sense, and it's useful for regularizing matrices. And then when we talk about the trace norm, and let's kind of go back to the slide from an earlier lecture where we have L1 and sparsity, right? In terms of regularization, sometimes we're interested in making our weight vector W sparse, right? We want there to be some zeros in W so that we're kind of intentionally making W sparse so that it doesn't overfit, right? So we're kind of helping it generalize by not making it less expressive, almost, right? By introducing zeros into W. But we can't do that by using the zero norm, the L0 norm, which, by the way, is not a norm. Like by the definition of a norm, you can't consider a norm. We just call it L0 norm, kind of casually. But L0 is like you count the number of zeros in W, right? But you can't optimize over that because it's not continuous. And so instead, we use, and again, going back to lecture 3 and lecture 4 when we were talking about regularization, instead we use L1 loss because L1 loss also induces sparsity. And here's the right term here, right? So it's the sum of, I think it's the sum of values of W, and then we have the regularization term. So we try to minimize that at the same time that we minimize our, this is what, regression loss, right? Squared loss. Right, so we have the squared loss, we have the regularization term, we're trying to minimize it. The regularization term is helping W be more sparse, have more zeros in them. So the trace norm we can interpret as the L1 norm of eigenvalues. And so we can kind of use it, again, in a similar kind of a way, where a matrix X is considered low rank if it has few non-zero singular values. So if a lot of singular values are 0, right, it's low rank. That's just the definition of rank for a matrix, right? And so, if we want to, if we have some model that has matrices inside, and we want to regularize so that that matrix is low rank, which we'll see again later, then we can't regularize on just the rank of that matrix because it's not continuous. So instead, we use the trace norm as its analog, because the trace norm also kind of encourages trace norm also encourages the matrix to have a lower rank, which again is, if you think back to how we talked about regularization in context of just like linear models, right? It encourages the model to generalize better by not overfitting and memorizing as much. Okay. Again, if the equations are confusing, don't worry, it's confusing to me too. But just at least building the intuition right now, and then going back to it and checking the math, that's totally fine. Okay. Let me make sure I didn't miss anything here. Oh, it's also convex. That's nice. Okay. All right, so these are some other useful properties that gets used in this field. We're not going to go over these one by one just because we don't use these in the later slides, but just know that they exist. If you've taken LinAlg, you've probably encountered some of these, and then there's some future classes that'll talk about this in more detail. But like Cauchy-Schwarz, AMGM, like it's very common. And if you ever need to prove anything with matrices, these might come in handy as kind of inequalities that you can kind of assume or disprove or contradict, right? You can show that something contradicts one of these inequalities or properties. So it's kind of useful in that sense. And then as well, once you get into more kind of complex, complicated fields like theoretical computer science or like computational learning theory, these pop up everywhere. So just know that they exist as matrix properties. I don't know if they show up in the homework or not, but maybe they will. So just know that they exist for now. All right, any questions on this portion? So again, we're just defining these norms so that we can use them later. Let me go back to this. So again, just know the top right section of this slide. Okay. I know it's boring. We'll get to the fun stuff. All right, again, so quickly recapping SVD and PCA. What slide is this? Oh, whoops. Don't do that. Okay. Again, SVD, we have that decomposition. PCA, SVD and PCA are equivalent. PCA is what we use to calculate SVD a lot of times. And then we can actually redefine, right, the condition of SVD using the Frobenius norm, right, the squared Frobenius norm. So we're just re-representing that residual before we had where we say, for some k, for some first k columns of U, we can transpose x into the subspace, transform it back, and the information lost, we can say we're trying to minimize the Frobenius loss, that the Frobenius norm of the difference between the original matrix and then this subspace projected matrix, and then projected back. Okay, so now we have the language to be able to talk about it that way. Okay? All right, let's get to the fun stuff. Latent factor models. So, this is also called matrix factorization. So or matrix factorization models. It's also called kind of, well, no, those two things. So if you Google this, actually, if you search latent factor models, I didn't get a lot of hits, but if you search matrix factorization models, you'll get more hits. So if you're looking for resources on this, I would recommend that. So let's set up a problem that we can talk about to kind of talk through this model. So this is called the Netflix problem. It was previously called the recommendation problem in the 90s and the early 2000s. Netflix took it over in 2006 because they were the ones that had the biggest problem in this sense. So let's set this problem up. So we have some users. So let's say Netflix is like building out their recommender system. Okay, so Netflix has M users, tens of thousands, hundreds of thousands, right? And Netflix knows what ratings they gave each movie that they've watched, right? So we can build this matrix of users and movies, right? What's one thing about this matrix that you immediately notice? Very sparse, right? Because every user hasn't watched every movie. So there's a lot of zeros in this matrix Y. Okay? So the kind of the goal that we're trying to get is we have this extremely sparse matrix where there's a lot of zeros. And not even zeros per se, right? Like NaN, right? Like the information doesn't exist. It's completely unobserved. Is it possible to use the values that we do have to predict the values in those sparse points, right? So kind of putting it back into the definition of this problem, can we predict what a user would rank a movie based on the movies that user has ranked already? Okay? So the kind of a classical way of doing this is with like nearest neighbors, right? So we can kind of plot out each user's ranking on each movie, and then we can say, well, that user is similar to all the other users that have ranked movies similarly. So that person's ranking on a new movie would be like, you look at the most similar user to that existing user, and then you take whatever rating they would have given it, right? That's kind of a nearest neighbor solution to something like this. But instead, by kind of posing it in this way, we can actually get we can do a lot better. The reason it's called a Netflix problem is because Netflix held a challenge for this back in 2006, going all the way up to 2009, where they offered $1 million to someone who could do better than their own model. And not like $1 million to a single team, but like split amongst like years and things like that. It ended in 2009 because some group finally came up with a methodology that did like 10% better than Netflix's own methodology. And that's kind of where this whole field arose out of, is that like one competition that Netflix held in 2006. Right, and so that's kind of where matrix factorization models became popular, and it's still being used. This whole methodology is still being used, just with a little bit more neural networks, just because neural networks take over everything. Okay, so there's some historical context there. Okay, so again, we have number of users, we have ratings for their movies. It's very sparse. We'd like to fill in the holes, right? That's kind of the overall goal. So this isn't supervised learning. It's not even unsupervised learning, right? You actually don't have any features. That's kind of an interesting thing about this problem. There's only labels, right? You can think of it as we only have the truth, and there's no features to describe anything, right? We don't have some user identity we can bank on. We don't have any movie identity we can bank on, right? We can't describe the users, or we can't describe the movies. The only thing we have here is which user ranked which movie a certain value. That's all we have. So it's kind of an interesting problem setup that we haven't seen so far in this course. Okay, the one last thing I want to point out about this kind of problem construction is what happens when Y is dense, right? So what if we did in fact have every user's ranking on every single movie? In that case, we can actually just use SVD to train a model, right? So we can actually come up with some U and some V, right? And we can treat this very kind of traditional. We can decompose this matrix all the way, right? And we can, this model can model everyone's kind of predictions for each movie. But because we can't do that, right, we arise with this kind of alternative model where using the existing values, can we fill in the blanks? Okay, so I should explain why we're doing this. So this is called an SVD-like model. Okay, so we're not actually using SVD here. We're just setting up a model that kind of emulates the SVD way where we have some U and some V transpose, right? But the trick here is that we have this dimension K, right? And that dimension K defines a lower dimensional subspace, okay? So again, we're taking this input data, we're projecting it into some lower subdimension, right? And then we're projecting it back with V transpose, okay? So each element in this matrix becomes So for example, if we want to predict some user's prediction on some movie, right? We just take their row in this matrix and that movie's row column on that matrix, and we multiply them and we get that prediction, right? The trick here is that the low dimensionality of this space allows us to generalize, right? So just training that model on the known values allows us to kind of almost extrapolate the values for the ones that are missing. Right, so we'll talk about this more. If you don't get it yet, when we kind of walk through this, you'll kind of understand. So the key here, again, is the low dimensional subspace defined by K. And this is from the original kind of AT&T, well, some part of the team was from AT&T. So this is from the original kind of big paper that came out of this Netflix challenge. But this is like a hypothetical example of what we can learn when we do this previous method. What it turns out is when you do a modeling like this, where you're forcing your data to be represented in a lower dimensional subspace, each axis of that subspace becomes expressive. It comes to indicate, like, it starts to have semantic meaning, right? So in this kind of hypothetical case, and this isn't real, like they're just kind of visualizing the point that they're trying to make, right? Let's say we ran the model, and afterwards, when we inspect just two axes of the many subspaces that we've learned, so we're looking at, you know, this k-dimensional subspace. If we just look at two of those dimensions, whoops, no. One of them, we might be able to say, well, this axis, you know, indicates whether it's escapist or serious, and then this other axis indicates whether it's stereotypically geared towards males or stereotypically geared towards females, right? This paper was written in like 2009, so we're still working on the PC stuff. But the point being, you know, we didn't come up with this. Someone didn't design this. This just arose out of the structure of the data itself, and then we can kind of slap semantic meaning on it after examining the subspace afterwards. And so we can actually say, you know, we can map users onto this space. So we can say, you know, these users prefer these types of movies. And then we can also project movies onto this space as well. And so we can say, you know, these movies seem to be exist here in this latent subspace. But the point here is that, again, we can project both users and movies onto the same latent subspace that has semantic meaning along each axis. Okay? And this arises out of the model itself. We're not designing this. Making sure I got everything there. So, again, coming back to the Netflix problem. Again, we have users, movies, and again, we can interpret these matrices as latent factors, where we're learning features for each user. So we're learning some feature k for each user, of dimension k for each user, and then we're learning some feature of dimension k for each movie. Okay? And again, the difficulty here is that there's a lot of sparse values here, right? So we can't do this just with SVD. We need something else. So this kind of a problem is referred to broadly as collaborative filtering. I actually couldn't find why. I'm sure there was some semantic reason initially for naming it collaborative filtering, but you can Google that afterwards. But it just is. It's just called, this class of problems is called collaborative filtering. So you have some number of users, some number of items, and you only have some small subset of pairs, right? You have a very sparse list of pairs, and most of them are missing. So this is actually, we call this the Netflix problem because Netflix tackled it with $1 million and kind of dominated that kind of research field. But you can do this for any user item rating problem, right? You can do this for e-commerce, right? You can do this for like serving user advertisement pairings, right? Like when Google tries to serve you relevant ads, like this is probably what they're doing, right? If you clicked on an ad before, it thinks that you like that ad, and so it tries to find other ads that you will like, right? It's kind of a similar problem. So again, the goal here of collaborative filtering is to predict those missing values in that extremely sparse matrix. All right, let's formulate this. Let's do this formally, and don't worry, I'm going to walk through this so that you kind of understand how we're presenting this problem mathematically, right? Or at least formally. So again, we only have labels. We don't have features. We only have what each user rated for each movie. We don't know who the users are. We don't know what the movies are like, right? Pure just labels. But using that, we can learn some latent representation over users U and movies V such that this is true. This is the optimization condition for a matrix factor model. Let's walk through this, okay? On this left side, we're trying to minimize everything, this whole equation, by finding some U and V, right? We're optimizing for U and V. And by the way, I drew this on the board on that side as well. As soon as you get confused about like matrix dimensions and stuff, just look at the board, okay? Because I get confused when I'm talking about it sometimes. So again, we're trying to optimize for the entire matrix U and matrix V, okay? And we're trying to optimize that so that for some held out set, or even the known values of ratings that we do have, right? So for some known value of y, which I labeled x here because I forgot, whatever. For some value that we do have, this reconstruction, so when we take one column here, and one column here, and we multiply them, that loss, that squared loss, is minimized. So in that sense, it's just linear regression on this end, right? Does this part make sense? It's just the squared loss of the reconstruction, multiplying u by v. Okay? Now this is actually the really important part. This is a regularization. This regularization term is required for us to generalize. You good? Who was that? I'm just kidding. So this part minimizes the reconstruction error for the values that we do know. But for the values that we don't know, we need this regularization term so that our model generalizes to values that we haven't seen before. If this didn't exist, we would find some u and v that spits out the numbers that we do know perfectly, given some big enough k, right? Given some big enough dimensions, latent space, right? It would reconstruct every y, every known y in the sparse matrix perfectly. But then all the unknown y values, like we would get nothing. We would just get zeros out. But because of this regularization, we can find some u and v that draws out structural information from this data that we do have and learns features for the users and movies. What these features do, we can actually, these learned features indicate which users are similar and which movies are similar. And therefore it generalizes, and we can start to fill in the gaps of the values that we don't have in this original sparse matrix. Yes?
Is k decided before we do the minimization, or is it kind of like encouraged to be low by the regularization?
No, k is defined. Yeah. So k kind of defines almost the complexity of the model. So if k is too low, you know, if k is 1, right?
It's kind of like a hyperparameter.
Yeah, it's exactly. It is exactly a hyperparameter. So it defines the complexity. So you need to set it beforehand. And there's no right answer for doing this, right? You can just do grid search, try all different values of k, and use the best one, honestly, on some held out validation set, right? So for the values that we do have, we would pretend some of them don't exist, right? Train it with some value k, and then provide another test set matrix with those held out kind of ranking values, predict them back, and see how well you did. Yeah, that's how you would set that hyperparameter value. Great question. Any other questions? Yes?
Like the k, do you have to choose like just values in the matrix, or could you like pick just a set of random k values?
Are we talking about when we initialize?
Yeah.
When we so we'll talk about optimization in a bit here. But yeah, you start by initializing these matrices randomly, and then you optimize towards that condition. Right? With gradient descent. We'll get there. All right. So again, we're finding u and v. to minimize the squared loss with regularization so that we generalize. Okay, that's the takeaway from this slide. Bless you. Okay, so we're going to connect this to the trace norm. Walk with me on this. So let's assume, okay, so we have this down, right? If you don't have this down, let me know, because otherwise the next few slides won't make any sense. Going once, going twice. Okay, cool. All right, so let's suppose that it's possible, given some k, just assume for the sake of this, assume that we have some u's and v's that achieve perfect reconstruction, right? And so you can imagine there's no one set of u and v that can perfect, like there's multiple u and v pairs that can have perfect reconstruction on y, right? So let's consider that we have some set, theoretical set, of all u and v that achieve this perfect reconstruction. We actually want, and the intent of this regularization term is to find u and v with the lowest complexity, right? So we want the simplest model, where our model is defined by u and v. We want to find the simplest model to reconstruct the data perfectly, right? Of the model set that reconstructs the data perfectly, we want the ones with lowest complexity, right? And we're doing this by defining like the Frobenius norm, right? And this is, you should be familiar with this. If you're confused by the Frobenius norm here, you know, in a linear model, this would just be the L2 norm of the weight matrix, right? We're just replacing this. We have two matrices in this case instead of just a W, so we're just adding them. And then we're just using the Frobenius norm as the L2 norm. That's it. That's how we're doing the regularization. So, turns out, finding this u and v with the lowest complexity, again defined by the Frobenius norm, is equivalent to finding some y with the complexity of that is equivalent to finding the trace norm of y, to minimizing the trace norm of y. So let me try and make that make sense. Optimizing this regularization value. So remember, there used to be a squared loss here, right? But that squared loss is 0 right now because we're assuming that this reconstruction is perfect. So we're just left with the regularization term. Turns out when you do this optimization, that's equivalent to estimating some y with the lowest trace norm. There should be a min here. That's what tripped me up. Okay. So again, remember that we define the trace norm as the sum of singular values. Sorry?
It should be minimal with the trace norm, is what you're saying?
So minimizing this is equivalent to minimizing this.
Got it. So
yes.
Yes.
Yes. I think I missed that. I think that's what tripped me up. So remember, we define the trace norm as a sum of singular values. So when we're minimizing the sum of singular values, we're also trying to find some y with the lowest rank, right? So if we're replacing rank with complexity, if we're trying to kind of equating those, this makes sense. So here's the proof in one direction. So again, we're trying to prove that these two things are equivalent. This is hard to derive. So if I asked you to do this out of nowhere, it'd be hard to come up with this. But if you actually went through this line by line, this is all just matrix algebra, right? To get from, minimizing that regularization term is equivalent to minimizing the trace norm of that final predicted y. Okay? Okay. And so again, the reason we're doing this, the motivation for this, is that a lower complexity model generalizes better, right? Is able to fill in the gaps better because it doesn't just memorize the data points that you have. That's the intuition. Okay, let me make sure I got everything on this slide. Yep, okay. Yeah. So the takeaway from this is that there's a strong connection between these norm definitions, where even if we define the regularization initially with the Frobenius norm, do some matrix algebra, we end up at the trace norm. Okay. There's also, according to Professor Yu, there's a strong geometric interpretation as to what is happening. I do not have that strong geometric interpretation with me because, again, I'm fairly new to this field as well. But like people write entire PhD theses on this, right? Like this is, if you're kind of into this theoretical definitions, then you know, there's a whole world out there that you can kind of search up. Okay, so using that information to kind of come back to the original model that we had, we have, again, the latent factor model objective. Now, we can't guarantee that this will be 0, like practically, right? For the sake of the proof before we did, but you know, this is always going to be there. That can very rarely be 0. But we can still see that this is related to finding some low rank approximation of y. So again, y we're saying is this matrix. I wrote x because I made a mistake, but optimizing this regularization term is equivalent to finding some low rank representation of y. Okay. So I personally think this is a lot more intuitive because we've seen this kind of structure before when we did linear models, right? You have some squared loss that you're optimizing for with some regularization term. But you can also think of it this way, where we're finding the best low rank approximation of y and decompose into u and v. Right? So if we just treat this as a completely linear model without this decomposition into u and v, we're just finding this w with the lowest rank. Okay? Yes?
Is there a closed form solution for this? Or?
Yes, we'll get to that. Yep. Good question. Okay, so there's an interesting symmetry to this kind of a model definition. So first, remember, we don't have any features, but we could treat it as features, right? So we don't start with any features of the users or the movies. But from the user perspective, if we treat the movie features as fixed, this just devolves into linear regression to learn u, right? So in that equation, if we fix v as a constant, we can just do linear regression to find u, right? And then also, if we fix u, then we can just do linear regression to find v, right? So again, in this kind of a structure, if this is fixed, if we know for a fact that if we're kind of assuming that our movie features are known, right? So we're assuming that these features indicate which movies are similar, which movies are different, right? Then we can just do linear regression to find u, and then vice versa.
You just keep doing that back and forth.
That is one way to do it. Yeah, we're going to get to that right now. We're going to talk about optimization. So we can take advantage of this to find u and v. There's kind of two ways of doing this. So what we're going to do, first thing that we should talk about is we're training over just the observed y. So again, this matrix is sparse. So for only the known values, where each known value is a multiplication of one row and one column, right? So you multiply one of these, you end up with that ranking. So we're only going to train to find, again, we're optimizing for u and v. So we're only going to train over the observed y values. And we can do that with either gradient descent or alternating optimization because there is a closed form solution. And this is apparently on the homework. I actually haven't seen the homework that we're releasing, so I'm not sure which question it's going to be.
Also convex, is that right?
Yes, that's right. Yeah. This only works because it is.
Mm-hmm.
And the norms are as well, right? Yeah, the norm definitions. Okay, so let's talk about the gradient. So, and I took extra notes on this because I also didn't get it on just based on this line. Let's think about gradient descent, right? For each point, and this is similar to gradient descent as we did before, for each point, we can calculate the gradient of the corresponding u, right? So again, this isn't the gradient for the entire matrix, right? We're only training on one data point, so it's only the gradient for one row, right?
So we can calculate for column. It gets confusing because of the transpose. But anyways, so for each u corresponding to that data point, that y sub ij, we can calculate the gradient for u, assuming that v is fixed. And in the exact same way, we can also calculate the gradient of v, assuming that u is fixed, right? So we're not alternating yet. We're not doing that. We're just calculating the gradient of u and the gradient of v for some given data point, known observed y. Okay? And then we can do this for every data point that we know in this matrix y, and we can optimize, we can do gradient descent to optimize the matrices u and v. Okay? Now the interesting thing here is every time you do this for each set, and then the same exact way that we saw this during gradient descent, like u and v are changing, right? So we're not calculating the gradients for all the data points. We can do stochastic gradient descent, where we update the matrices as we see each data point. Okay? Does that make sense? Gradient descent? So we're doing gradient descent optimization to find the best u and v to solve that optimization term. That's regularized. Okay. Now, as you mentioned, there is a closed form. Because this is just linear regression, there is a closed form that you can solve as long as you invert this massive matrix. But it is possible, right? So taking advantage of that, wait, hold on. Let me finish talking about gradient descent, and then we'll get to optimization. But again, so for stochastic gradient descent, we update all the parameters for a single data point. There's an alternative to this called alternating SGD, which I don't think is as important personally, but we'll still cover it, which is instead of training per data point, we train per column. And we can do that because we can say, okay, what are all the data points for that column? Calculate the loss on all the data points that are associated with that column, and then update that column, right? So this is just kind of, I think this is just kind of a more of a computationally faster way of doing this, because if you're going data point by data point, that's slower than if you're updating entire columns at once. So it's kind of a pseudo-parallelized version of like original stochastic descent, right? Okay. So again, it's just SGD. It's with like the previous formulation we had in like lecture 3 and lecture 4. It's just a little bit more complicated because we're dealing with u and v, so we're dealing with two matrices that we need to update, and we have this extremely sparse matrix, right? Okay, got it. Next, because we have this closed form, we can instead do something called alternating optimization. So alternating optimization, we start by initializing u and v randomly. We fix v, and then we solve for u, right? Using the closed form solution. And then we fix u, and then we solve for v using this closed form solution. And we go back and forth until we're not updating anything anymore, until they converge, right? So this is kind of similar too to kind of the clustering algorithm that we talked about before, right? Where we fix one thing, we update one thing, and then we fix that, and then we update the other thing, back and forth and back and forth, right? So this only works because there's an optimal solution. It is an expensive optimal solution, but it does exist, so it is possible. Same way in the gradient descent problem, where an optimal solution did exist, but it's just really computationally complex to do that, right? Okay, and then I guess this is mentioning that you can also do this on a column-wise basis instead of like doing the entire matrix at once, which kind of helps reduce your computational complexity. But again, it's just we're alternating the optimal solution back and forth until it converges.
So gradient descent just like a more computationally proper way to do this.
Right. So gradient descent is like an estimation of the closed form solution. Right? So yeah, I think the interesting thing about alternating optimization is it's more parallelizable, right? Because gradient descent, like stochastic gradient descent, depends on the previous kind of optimization step to go on to the next one, right? Whereas alternating, you can kind of do these at once. We can like combine some of these steps, so it's more parallelizable. Also, for alternating optimization, each update uses all of the ratings at the same time. So it uses all known values at the same time to make each update, right? Because it's a closed form solution. And so it arrives at the solution a little bit faster. But again, if your data set is massive, then it's not going to work. So in the industry, most of the time, you'll see that they use stochastic gradient descent. Oh, that was this slide. Yeah, so exact thing I mentioned, where it's in terms of number of flip-flops you have to do, alternating optimization is a lot faster because we're actually solving the closed form solution, but this is impossible if your data set is massive. Gradient descent, much faster for high demand. If this matrix has like 10,000 users, 100,000 of users, gradient descent is often your only solution. You can also stream data. So if you do alternating optimization, you need to store this entire matrix in memory when you're doing your closed form solution. But for streaming, you can just feed it one data point at a time. And so you save a lot on computational memory. Okay? Okay, so this is, okay. All right, so this is kind of the result from that same AT&T paper. Hold on, let me make sure I didn't miss anything. Yeah, so this is a visualization of the actual latent factors that were learned around, and so they picked the movie Wizard of Oz as a reference point, because this is all relative, right? And so they're saying, here's where all of these other movies map based on these two latent factors that we've learned, right? So it's like that previous graph I showed, except this is actually derived from an actual model. So it's hard to put, again, a semantic label on these axes, right? Because this is what some computer came up with. But if you kind of go through it, you can see at least movies that are next to each other are similar in genre or style or something like that. I think we can say that. Let me see. I think we can say that like the Fast and the Furious is definitely like opposite of Lost in Translation, right? So at least we can look at opposite points on this, and we can see, okay, the latent factor did learn some semantic features. It learned that movies are similar or different, but again, completely based on just user ratings, okay? Without any information about the movie itself. So that's interesting and useful for companies like Netflix. Okay? All right, just to recap. Again, we've talked about this collaborative filtering. How much time do I have? 20 minutes? Yeah, okay. All right, we're going to burn through these next couple slides here. So again, we've talked about collaborative filtering. The goal is to predict every user item rating pair. But the challenge is that we only have a small, sparse data set observed. And so the assumption, again, this is critical. There's some low-rank subspace that defines Y, right? And this subspace is capable of capturing all the variability and describing the different users and items. So it's this low-rank subspace that allows us to generalize, and fill in the gaps in the rest of the matrix. Okay? Any questions about this collaborative filtering? No? It's interesting, right? It's kind of an interesting, different kind of a problem structure. And it's interesting that we can construct the problem in this way to be able to solve it. All right. So, quick aside into multitask learning. I'll go through this fairly quickly. So forget everything. Forget about matrix factorization. Just forget about all that real quick. Let's just talk about multitask learning. This is another kind of formulation of a problem where, in this case, we do have features about the movies. We know what the movies are like. We have some feature description of the movies. So what we need to do is, for each user, we need to provide some personalized recommendation. Okay? So this is called multitask learning because the thing that we're optimizing for, and we don't even have the decomposition. We're just talking straight linear model. We just have some W, right? So we're trying to find some optimal W, but we're trying to do this for each individual user, right? And so each user is different, so we need to provide a different movie recommendation based on known movie features. That's in the X. Okay? So given some common movie X, we want to predict a different Y, recommendation Y, for each user X. Okay? We call that multitask learning. It's very popular for kind of personalized recommendation systems. But what we're kind of assuming here is that so we could train a different model per person, right? That's entirely possible. But the concept is that if we regularize on W and we make W like less complex, there's actually some shared we're kind of assuming, hypothesizing that there's some low rank structure here where we can share information across user models to help each other. There's some common knowledge that binds all the users together, but we can still provide personalized recommendations for each user. Okay, so that's kind of the concept that we're going through. So how do we regularize? We need to regularize W so that the model generalizes across users, right? And we share some kind of low rank information. If you just use the standard L2 norm, this actually doesn't work because it immediately decomposes down to independent tasks. So if we just use the standard L2 norm to regularize W, this is actually equivalent to just learning a different W per user. And we don't want to do that because we want to have some common knowledge amongst all the different users. Yeah?
Okay, what is this big W matrix?
It's just a linear model. Our prediction is literally WX. Yeah. So we're not doing this yet. We're not doing this. It's just some linear model. Okay. So given some, so given some movie feature and given some weights, we're trying to predict some recommendation for each user. But each user is different, right? So again, one way of doing this is to just use L2 norm, but it immediately decomposes. So we just end up learning a different W weight per user. So this is just the equivalent of doing a different task for each user instead of learning one big multitask model, which is what we're trying to do. Okay? So because this decomposes to independent tasks, we can't use the L2 norm. The L2 norm doesn't actually help us learn some subspace where we can share information between tasks. Instead, if we use the trace norm, we can induce W to have a low rank across all the tasks, right? So what that means kind of intuitively is, I wrote it down. Just a second. So suppose that if we can encourage this W weight matrix to have low rank, we're kind of assuming that the variability of users and interests vary in a low dimensional subspace, right? So we can describe the variability of the users in some lower dimensions, and that means that we can share information across the users, right? There's similar users behave similarly, right? That's kind of the assumption that we're making. We can describe this similarity between users in a lower dimensional subspace. Okay? So instead we use the trace norm, which induces W to have a low rank across all tasks, which means W shares some information. W is encouraged to share information across tasks instead of just learning an individual weight vector for each task.
I don't really get why this task appears different from this, because in this case, like, we can still generate a ranking, right? We can just take one row for this user and then.
So in this case, so for the Netflix problem, we only have ranking. But in this case, we do have some known features for movies, and we'll get there. This decomposes into this. So we'll get there. But for the sake of this, we're just doing, we have some weight W, and we have, and then we have X, right? Can we predict some Y?
What is this X?
This is the movie features, or whatever media that we're recommending. So we've already described the things that we're trying to recommend in some space. We're not trying to learn this. This is given. We're just trying to learn some W mapping for each user. So this is each user to predict something.
And then the X is a 1 by.
Whatever, yeah. Well, it can be any dimension. This is given. We're just assuming that this is some given description of movies, right? And then this is like a list of users. So like user 1, user 2, user 3, user 4. Right? So an easy way of doing this is to just treat each of these separately, right? So if I just do some user, some movie descriptions, give me a prediction, I can do that. I can learn all of these user weights independently. But if we treat it this way and we encourage W to be low rank, it actually learns some general subspace projection of user information where we don't have to actually learn different parameters for each. We can kind of learn user features that encourage us to kind of, this model generalizes, and it better generalizes to new users. So even if we include new users here, right, like because W is low rank, it can do a lot better. Does that make sense?
Right. So it's like technically worse than.
Well, worse in what sense, right? It might be worse per users, but
on
we're
average, yeah.
right. We're aiming for generalization.
And it's way faster.
Yeah. Well, it can be faster. That's right. Yeah. Okay. Did that also make sense to everyone? That made sense to me as I was explaining it as well. So hopefully that helped. Okay. So if you recall, this previous slide we had where we showed that the trace norm is equivalent to this other regularization term defined by the Frobenius norm. Okay, so we can actually plug this back in, and we can convert that problem into a latent factor approach, right? Because we can represent this multitask problem in this way using W and the trace norm. We can convert this back into a latent factor model. Got it? Does everyone at least see how it plugs in? Right? Because of this? So we had this before. We showed this earlier. And therefore, we just plug in, we replace the trace norm of W with this regularization term. Right? And therefore, W also becomes U times V times X. Okay? So we basically converted this formulation back into this. But the difference this time, I should have just done this over here. I don't want to keep walking over here. The difference this time is one of these is known. This is X, right? And so, you know, we're learning a different decomposition. Right? We started here because this makes sense, and we're showing that we can deconstruct this back into the structure that we had before. Okay. So the trade-off here is that in our original kind of way that we had it, we had to learn D times N parameters, right? So we had to learn this W vector, and the dimensions of that W matrix was D times N. But when you deconstruct it into this U times V, we actually only have to learn D times K and N times K parameters, right? And so when D and N go up, but K is fixed, because K is the subspace, remember? Right? The complexity of this is much lower than the complexity of learning D times N. Make sense? We're just making a complexity argument. This only works if this low rank assumption is good. Right? So again, we're assuming that this low dimensionality subspace defined by K is enough to describe the users and describe the movies, right? But that has to be good in order for this to work. If it's not good, if this lower dimensional subspace isn't good at all at describing anything because it's so complex, then this won't work. Got it? Okay. So, again, going back to multitask learning, this is our new construction now. We have, now we're back to learning U and V. So the example that we keep using is this personalized recommender system, where we have one task per user, and X is some topic feature representation, so X exists, again. V is a subspace of correlated topics, and it projects multiple topics together into some latent subspace, okay? Yeah. Does that make sense? So this is different from the ranking problem, right? This is different from the Netflix problem. This is, you know, the movie features are known, but we're trying to give a different recommendation for each user. Right? So we start with that linear model representation, but we show that because we're trying to make this W, low rank. Trying to make this W low rank is equivalent to just trying to learn U and V with subspace definition K with the previous regularization term that we had. Okay, that's kind of the intuition. Oh boy, 5 minutes left? Okay. I might have to upload the rest of this lecture online, but we'll get through as much as we can, okay? Okay, so as we showed, this reduces to collaborative filtering. So describing this multitask structure in terms of collaborative filtering, suppose each X is just a single indicator, right? So instead of having features for each movie, we just one-hot encode what each movie is. Then this is just the same problem that we had over here. Okay, so before, with the multitask learning, we were assuming that we knew something about the movies. If we don't know anything about the movies at all, we can actually learn it. And so that problem up there decomposes down to collaborative filtering. Okay, so multitask learning is just collaborative filtering where we knew something about the targets. If we don't, then we can just do collaborative filtering instead. Got it? Okay. So again, which is which? U transpose Y. Yeah, okay. So again, for latent factor multitask learning, it projects some X into low dimensional subspace E times X, and then it learns a low dimensional model per task, right? So per user, it learns a low dimensional model. But if you don't even have X, then it creates that low dimensional feature for each movie, and then it learns a low dimensional model per user. Okay, so the difference is what's given, right? So for collaborative filtering, nothing is given. We have no features, just labels. But for latent factor multitask learning, something is, at least some features of the movies is given. Got it? Okay. So this generalizes even further to bilinear models in general. So we have some users described by feature Z, some items described by features X, and we're learning a projection of Z and X into some common low-dimensional space, and we're learning a linear model in this low-dimensional space, right? If we don't know anything about Z and X, then it becomes collaborative filtering. If we just know X, it's that multitask example, and if we know both Z and X, we can kind of generalize that as a bilinear model, okay? But again, the core concept of this is that we're projecting both Z, users, and X, movies, into a common low-dimensional space where we can train a linear model. Got it? Okay. This is kind of the punchline of this. This whole thing generalizes into this one common problem structure where we can solve these problems. So again, bilinear models are useful because of the dimensionality problem, right? Because we have this K here, we don't have to learn as many parameters, right? We can just learn m times k times n times k, or et cetera, instead of learning the full linear model weight matrix, right? Because we're again making this assumption that this smaller subspace, low dimensional subspace, is enough to describe our problem. We don't need every single dimension. Okay. All right, again, kind of burning through these. I just want to get to non-negative factorization before you guys leave, and then we can kind of, I'll keep talking up here, and then you can leave early and you can watch the recording later, because I don't want to keep you for longer than I have to. But yeah, I'm taking a long time describing these because I'm also kind of processing this information as we go along. Because again, I also went through these slides like yesterday. I don't have a background in this, so sorry about that. Okay, so the story so far, again, these latent factor models, remember, if we don't have any missing values, this reduces down to SVD, right? So if Y itself is complete, then this is just SVD. But if we don't, and in a more general case, we're creating these SVD-like models where we're not doing SVD on the data itself, but we're kind of setting up the deconstruction similarly to SVD, where we assume that this high-dimensional representations can be represented in a linear model in a lower dimensional space of dimension k. Okay? And then we're optimizing to find U and V instead of using SVD to find U and V. Okay, so that's what we're trying to do. As a quick aside, you don't have to have linear projections. So we're using U and V as linear projections of users into some K subspace and movies into some K subspace. You can also use neural networks to do this exact same thing. And this kind of gets described as Siamese models. It's very popular, especially for images, but you kind of end up with this case where you have a lot more expressivism because you're not using linear projections anymore. So in this case, they like scrape to Amazon data, and so this is like a fashion embedding. So like what kind of clothes go well with each other. And so because they can learn a nonlinear mapping of images of clothes into a smaller subspace, they can now kind of find which clothes go together. Okay? All right, so again, sorry for going long. I will finish this lecture by talking about non-negative matrix factorization, and I'll put that online tonight or this afternoon. I'll do it as quickly as I can so that you don't miss out on non-negative matrix factorization. Thankfully, this is a lot easier than all the collaborative filtering stuff that we've been talking about. This is just PCA, except we forced all of the values to be positive, and they don't have to be orthogonal. So instead of learning PCA and SVD, learning this orthogonal projection, we can have any kind of non-orthogonal projection, and so we can describe the data better. And they're also non-negative, so it's easier to visualize. That's it. I'll actually finish this lecture once you guys are gone. Okay, thanks. So we'll take a break here. If you need to leave, please leave. If you have questions, come up and ask me questions. I'm gonna cut this out of the recording, and then I'll attach the rest of this lecture and upload it online. And for the recording, all right, so we'll start talking about non-negative matrix factorization. So previously, we did PCA and SVD, again, to learn these orthogonal basis vectors, right? So this orthogonal matrix, where we can project our data into a lower dimensional subspace, and it was guaranteed, right, that these axes that we found, these orthogonal axes that we found, capture as much of the variance in the data as possible, right? But because of the limitation that they have to be orthogonal, right, what happens is that these axes are forced to be perpendicular. So for some, and this is a kind of a contrived example because we're forcing it to be bad, but you can imagine that there are some cases where orthogonal vectors are not actually, orthogonal axes is not actually what we want to capture the most information possible about the structure of the data, right? In some cases, we want, I guess in this case, vectors like these to describe the data because it better fits the structure of the data, right? Another point about this is that when you do PCA and SVD, you inevitably end up with vectors that are negative, right? And so you can kind of think of it as, you know, unless your basis vectors are like 1, 0, 0, 1, right? As soon as you try to rotate this in any direction, you have to end up with negative values in one of these, right? So you end up with negative numbers. And so in some cases, it's actually not, we don't want negative values in our kind of what were previously eigenvectors, right? Eigenvectors have negative values. So we want to do this without arriving at negative values, maybe because of the data, maybe because of visualization, right? We're trying to interpret these results. So it becomes of interest to instead find some latent factors of y that are non-negative. And so what we need to do first is assume that y itself is non-negative, because we need that in order for this to work. And then what we're going to optimize for is finding some non-negative u and v that decomposes, you know, this original matrix y into those latent factor models. And so this is kind of, because we're not setting any constraints that the columns of u have to be orthonormal, right? We can find positive or at least non-negative representations that are easier for us to interpret or fits the data better. So as kind of an example, this is the eigenfaces example again, but this time we're using non-negative phase spaces, right? So previously when I showed the PCA example, we kind of had these ghost faces, right? So these are the eigenfaces for this data set. And the problem with this is that, you know, in the eigenvectors for these faces are negative and they're all over the place, right? And so I have to apply some kind of a color map to these values to kind of have to visualize them in this way. But if you just do non-negative non-negative matrix factorization, then we can actually end up with more semantically meaningful phase spaces, right? So these aren't eigenfaces anymore. These are just non-negative phase spaces. And so because the values themselves are positive, it makes a lot more sense to plot them out or visualize them in RGB space. And so there's other examples such as so there's some examples inherent to data. I think this is fairly popular in the medical sense because our body isn't negative, so data that we measure from our bodies doesn't end up being negative. And in a medical sense, you want to interpret the results that you get from PCA, but you can't if the numbers are negatives. And so they instead use non-negative phase spaces. I just read that on Wikipedia, so I don't actually know if that's true or not. But at least that's one example of where, because your data is guaranteed to be positive, you need to interpret the results. It becomes of interest to find axes that are also just all positive. So again, non-negative phase spaces, eigenfaces. This is easier to interpret because RGB values are inherently positive. Okay? So, as a quick aside, you'll notice that because we're finding bases are not orthogonal, A transpose A is no longer the identity matrix. So, once we found some UV, right? We use U to transpose project, right, the original data into lower dimensional space. But how do you project that back, right? Because with PCA, we could project it back. It's perfect, right? In this case, we actually need to use the pseudo inverse, and I won't get into that now. But basically, it's the inverse of a matrix that shouldn't have an inverse, right? So it's some inverse estimation of the matrix. And so again, for U that we found during PCA, U transpose is equal to U inverse, right? Because it's orthonormal, and so this was easy to do. But now instead, we need to use the pseudo inverse to project that low dimensional representation back into our original space again, because the bases aren't orthonormal. Okay, so this is just a kind of a not minor point. It's pretty important, but it's explaining how to do this when U transpose doesn't equal U inverse, or an inverse might not exist. You use the pseudo inverse. I won't get into how to calculate the pseudo inverse because that's you can cover that in linear algebra. Okay, so very similarly, this is the objective function. So we're finding. So given that U and V, so again, we're sticking with the problem statement that we had before, fixing U and V as non-negative values. We're trying to find the values of this matrix that minimizes the loss after reconstruction. Okay, so it's an optimization version of PCA where we're trying to directly estimate the matrices U and V while locking them to be non-negative. Okay, so we're trying to optimize our way into learning U and V instead of using SPD or PCA, right? Because that allows us to find non-orthogonal bases to do this deconstruction. So the loss function to do this, we talked previously about squared loss, and we used that previously for the collaborative filtering problem. There's also a thing called generalized relative entropy, which is the same thing as the unnormalized KL divergence. We can do this if we take a probabilistic interpretation of this objective function, but that's not that important. Just know that there was a Nature Communications paper in 1999 that basically said, this works pretty well, so it's kind of a common method to use that. You can read that paper if you want to see what that probabilistic interpretation is, but it's a little complicated for me to really get into. You add the Poisson noise to the probability of generating. Yeah, no, I'm not going to get into that. But anyways, that is a common thing that people do, and that is what Professor Yisong used to do the previous non-negative phases. So just know that that exists. And then again, same thing that we did with collaborative filtering, we're just trained using gradient descent. Okay? All right. So comparing SPD PCA and non-negative matrix factorization, singular value decomposition in PCA finds the best orthogonal basis spaces, basis vectors, faces in the eigenfaces example. But again, the coefficients can be negative, which makes it hard to interpret. It's trickier to visualize because it's negative, right? But you do get a better reconstruction because again, PCA and SVD guarantees that the orthogonal basis that it finds captures as much of the variance as possible. Whereas with non-negative matrix factorization, in exchange for getting non-negative coefficients and non-orthogonal coefficients, which might sometimes better represent the data, we don't have that guarantee anymore, right? We don't have the guarantee that the bases that we find are like the most optimal. We're just doing gradient descent to find like some local minima. And so oftentimes you'll need more basis vectors. That K will need to be larger than if you were to do with PCA to minimize the residual. Okay. So you can extend this to non-negative latent factor models where instead of going back to the latent factor models that we discussed before, we also restrict the values in U and V to be positive, or non-negative. So it reduces, in the simplest case, it reduces non-negative matrix factorization of matrix Y. If you have no missing values and ZNX indicator features, it just reduces straight to the non-negative matrix factorization. And in the general case, again, we're just building intuition here. It projects the high-dimensional non-negative features into low-dimensional non-negative linear models. So again, just go back to what we talked about before with the, not the latent factor models, but general bilinear models. It's just general bilinear models, but with non-negative values. That's it. Okay. Okay, so this is Professor Yisong's project and I think, again, this is why this kind of this section is in the curriculum, is because he's very familiar with this. I actually never learned this in college because it's very specific to recommender systems. It is very popular in industry, and this is very common. And the kind of a different part of this, metric learning, is very popular for certain problems. But I actually personally never covered this in college, so I had to relearn this. But this is a very interesting thing where he's modeling NBA gameplay using non-negative spatial latent factor models. So this is like paper that he and his students published, I assume. So what they did is they modeled a baseball court as 1 by 1 foot cells, and so you end up with 2,000 cells around like the basket, right? And then what they're trying to estimate is, at least in this sense, where does each player shoot from, right? Like a heat map of where each player's shot from. So this player in the image here is who? I wrote it down. Oh, Tim Duncan. Sorry, I don't watch basketball. It's also from a while ago. So, but anyway, so this is Tim Duncan, and so this is the heat map of all the places that he's shot from during like an entire NBA season. But the problem is that most players actually haven't played that much. So for Tim Duncan, who's fairly popular, you get this kind of dense heat map where you have a lot of data to go off of. But for a lot of players, they haven't played that much, and so we need some other representation to give it. What's interesting for me is that this is fairly old. So this is pre-2015. So I think this is the 2012 to 2013 season. So you can see that a lot of the shots were inside of the three-point line, because I think the strategy back then was to shoot as often as possible and be able to kind of maximize your chance that you're going to at least score. But since like 2015, 2017 season was Stephen Curry at GSW, right? You'll see these heat maps in the modern NBA days. Most of the shots are taken from outside the three-point line to score as many three-point scores as possible, because players have gotten better at scoring three-pointers. So this heat map will look completely different for a modern NBA game, but kind of an interesting sports trivia kind of statistics there. Anyways, so what you can do is, because again, you don't have dense data for most players, you embed the players and you embed the court space into this latent factor model. And so non-negative latent factor model. And when you do this, you can actually come up with, these are each of the, what were previously eigenvectors, right? No longer that, non-negative basis vectors. So these are now basis vector representations of what makes up these heat maps, right? So these are components of the heat maps, but they're non-negative bases. And by doing the linear combination of these bases maps, we can produce the kind of the heat map for each player, even if they haven't played that much in the NBA, right? Because we have some lower dimensional embedding for each player, and we have the lower dimensional embedding for each court location relative areas. And by doing that, we can kind of estimate where each player shoots from, even if we don't have that much dense data to go off of, because the model has learned in some lower dimensional space which players are similar and which shooting locations on the court are similar, right? So now we have a linear model in this lower dimensional space, and so we can learn this a lot better. Okay. So again, the training data, this is really interesting. They like mounted some cameras on top of the basketball court. They have some training data, 630 games, 380 frames per possession, which is pretty good. And then they're trying to predict a lot more than just where does each player shoot from. They're also trying to say, for each game state, is this player likely to shoot? Is this player likely to pass? Where are they likely to pass to? Et cetera. So this overall project is to predict some event based on the current game state, and they do this by taking advantage of this latent factor model. And so if we kind of look at this just in the shooting sense, right? We're trying to learn this mapping with I think this is logistic regression with log loss, right? And so, they could predict this directly, but again, there's not enough data. So instead, they're using again a non-negative latent factor model to do this in the K lower dimensional space instead, and they do a lot better when they do that. Okay, so I'll kind of go through these again. It's just log loss, but in the non-negative space. Again, same thing. You do optimization via gradient descent. We already talked about this, so we're kind of bringing everything together. And so finally, you kind of get these results where you can ask questions like, where are players likely to receive passes, right? So again, these are the factors, right? So these are the lower dimensional representations of the court spaces, and then you can generate these heat maps for where each player is likely to receive a pass. And then you can even do this not player to player, but location to location. So you can say where are passes likely to initiate and where are passes likely to end up, right? And then so you can generate heat maps such as when you pass from wherever X is on this map, where is it likely to end up? And if a pass ends at a certain location, where is it likely to be initiated from, right? So again, the power of kind of learning everything in this low dimensional space allows us to create very interesting heat maps like this, even if, again, we don't have data for every pass that initiates from this point, right? We don't have enough data to generate this normally. But instead, by learning the lower dimensional representation, we can kind of extract this out of the small amount of data that we have. Okay, finally, 2 more minutes. Tensor latent vector models. We can do this with tensors. So we've been talking about the 2-dimensional case before. We can do this in 3 dimensions, 4 dimensions. The matrix math gets a lot more complicated, but you can. That's the point. And so you would end up with kind of a trilinear model where instead of just U and V, you end up with U, V, and W, right? And so this might be interesting, for example, for online advertising, where it's not just user and item. It's user, what did they search, and based on what each user searched, what should we recommend? So like on Amazon, if you search something, you don't just get the results, you also get like advertised recommendations, right? So you might use something like this for that. All right, last slide. So finally, took me an extra 20 minutes, but we got there. So again, we have these latent factor models. They're very powerful, and that kind of power comes from the fact that it learns a low-rank model of a matrix of observations Y. So it's this K, it's this lower dimensional subspace that allows this model to generalize even in the face of sparse observed values. And so it can tolerate missing values in Y. But if we do have existing features, if we don't just have labels, if we do have features, we can incorporate that into the model, and we can still use that to make the predictions. So again, it's used very widely in the industry. Nowadays, it's some form of this mixed with neural networks because again, neural networks are very powerful at generating feature representations of items. And so, instead of just using the ratings, right? So before Netflix had to just rely on user ratings on movies. Now we have some deep learning model that can represent movies as features, right? So it can summarize a movie in a sequence of numbers using some neural network, and then that way, we're not just doing this from scratch. We're doing the kind of multitask learning before, which helps the model do a lot better because you're adding prior information from these neural network models. All right, I'm glad we got through that. Thanks for staying extra late, and thanks for watching extra late, the extra long video. Next lecture, we'll talk about embeddings and word-to-vec, which gets, again, very interesting. And yeah, thanks.